In the last chapter, we concluded by talking about angular acceleration. And in this chapter, we will discuss what causes that angular acceleration. The objectives for this chapter include understanding the relationship between torque and the three variables which make it up, understanding the difference between torque and force, being able to calculate the torque on an object, and finally being able to calculate the net torque on an object. We have seen that a force causes a linear acceleration and that a centripetal force causes a centripetal acceleration. So what kind of force or quantity causes an angular acceleration? To understand this, let's investigate the rotation of a simple object. In this case, the rotation of a door as it is opened. In this diagram, we are looking down at a door. The red dot indicates the hinge of the door, which we will call the pivot point when we are working these types of problems. The green arrow represents a force that is pushing against the door. Now obviously, when we push on the door, it will slowly open. Now we have a larger force pushing on the door, and as you would expect, it causes the door to open much more quickly. This leads to the conclusion that a larger force is more effective at producing a rotation. Now let's see what happens when we change the position at which the force is applied. Here we have our original force, and it opens the door at the same speed it did before. But now we have a force that is closer to the center. And when we try to push on the door with this force, it takes a lot more effort just to get that door open. You can try it yourself on any door and you'll see that I'm telling the truth. This leads to the conclusion that a force farther from the pivot point is more effective at producing a rotation. When a force is directed straight along the radial line that runs through the pivot point, there is no rotation produced. It does not matter how hard you push against the edge of the door, it still won't open. Any force along that radial line, whether it is a push or a pull, will not cause a rotation. In fact, a force directed along any line that runs through the pivot point will not produce a rotation. Now let's look at the direction of the force. What if I'm unable to push at the door straight on because something's in my way, like a baby rhinoceros? I will need to direct my force at the door at an angle. Because of this, it is much more difficult to open the door, and I cannot rotate the door as effectively as if I had pushed at it straight on. Let's see what this means, but first let's get that pesky rhino out of the way. Now this force is directed at an angle, and because a force is a vector, we know that it can be resolved into a horizontal and a vertical component. Here the horizontal component is the blue arrow, and that arrow acts parallel to the radial line that runs through the pivot point. Because of this, the blue arrow has no effect on rotating the door. The orange arrow, however, does act straight on at the door, and so it is the only part that causes a rotation. So this leaves us with the conclusion that only the perpendicular component of a force produces a rotation. So now we see that the ability of a force to cause a rotation depends upon three factors. First, the magnitude of the force. Second, the distance from the pivot point. And third, the angle at which the force is applied. Together, these three factors make up the quantity we call torque, which we can loosely define as the effectiveness of a force to cause an object to rotate. The symbol for torque is the Greek letter ta, which sort of looks like the symbol for pi, but with only one leg. Now let's put together what we know about these three quantities to create an equation for calculating torque. First, we know that the force is directly related to the torque. The greater the force, the greater the torque. So we can put an F into our equation. Next, we know that the distance from the pivot point, or what is known as the radius, is also directly related to the torque. The further the distance, the greater the torque. So let's put an R into the equation. The final factor in determining the torque was the perpendicular component of the force. In order to figure this out, let's look at the triangle once again. Now the orange arrow is the perpendicular component that will produce the torque in the object, and we find this by using this angle called phi. Because the orange angle is opposite, we can tell that it is F sine of phi. Because we already have an F in the equation, all we have to add in is the sine of phi. Let's take a second to look at this angle phi a little more closely. Where it's positioned here in this diagram is not where it will be shown or discussed in problems that you solve. However, because we took geometry, we know that alternate interior angles are congruent, and so this angle up here is the same angle. So that is the angle we will be looking at when we solve these problems, and that is the angle that the force makes with the radial line. So now we have our equation for torque. That torque is equal to Rf sine of phi. And it doesn't matter if you've got a force that's pulling really far from the pivot or a force that's pushing at a different angle up closer. This is the equation you will use to find torque. In many torque problems, the force is directed perpendicular to the radial line, making a 90-degree angle. And because the sine of 90 degrees is 1, in the equation, the sine of phi just becomes 1, and so we can take it out. So for any force that is already acting perpendicular, the equation becomes torque is equal to radius times force. Torque is a vector and so has a direction, which is indicated by either a positive or negative sign. Now you could probably already guess that if it moves an object in a counterclockwise rotation, it's positive, and if it moves an object in a clockwise rotation, it's negative. Take a minute to check out this diagram, which comes from your textbook. This diagram shows various torques that would be applied to a wrench. Now if you'll notice, the two that act along the radial line produce no torque, whereas these two on top try to turn the wrench counterclockwise, so they would be positive, and the one that's perpendicular would be the maximum positive. Likewise, the two on bottom, which are attempting to rotate the wrench in a clockwise direction, would be negative, and the perpendicular one would be the maximum negative torque. The last thing to discuss in this video is what happens when there's more than one torque. Now we have seen in linear motion that if there are two different forces being applied to an object, we find the net force by adding up all of the forces acting on the object. We apply the same principle to torques. Here we have a force acting at a short distance from the pivot point at an angle of phi, and we can find its torque as torque 1 equals R sub 1 F sub 1 sine of phi sub 1. We're just using the equation for torque. Next we have a larger force acting at a greater distance at another angle phi 2, and we can find its torque by multiplying the radius times the force times the sine of that angle. We can then calculate the net force by adding up these two torques. We need to remember that the first torque is negative because it will move it in a clockwise direction, and the second torque is positive because it will move it in a counterclockwise direction. That completes this video on torque and the basic principles behind it. Be prepared to answer questions and solve problems when you return to school.